Before we investigate the shell model of electronic structure, it is worthwhile to quickly recap what we know. Atoms contain protons, neutrons and electrons. Protons and neutrons are found in the nucleus, electrons outside the nucleus. The volume of the nucleus is only a small fraction of the total volume of an atom. Thus, nearly all the mass of the atom is contained in a densely packed nucleus, and the overall atom is largely empty. Rutherford was never able to incorporate electrons in his model in a way that would explain the observations of atomic behaviour, such as atomic spectra. However, his graduate student Niels Bohr could. Bohr's idea was that an electron was held in an atom by the attraction to the oppositely charged nucleus. He made several assumptions. The electron travels around the nucleus in a circular pattern, in an orbit. Second, the energy of an electron is proportional to the distance from the nucleus. And third, only orbits with certain energies are allowed, i.e. the energy is quantized. Thus, when electrons move between shells, it involves the gain or loss of energy depending upon whether they move towards a lower energy shell and energy is lost by the atom, or to a higher energy shell, in which case we have a higher value of shell and energy is gained. The energy lost or emitted is manifested as a frequency or wavelength of electromagnetic radiation according to the equations delta E equals NH nu or delta E equals Hc over lambda. Although no longer valid, Bohr's model is helpful in explaining some properties of atomic behaviour. Now the questions are, as we move from element to element, we add one more electron. So if we add one more electron, to which shell does it go into? And for whichever shell, how many electrons go into that particular shell? Before we can build up the rationale for the electronic model in an atom, there are two things we must look at first: Coulomb's law and ionization energy. Coulomb's law provides a measure of the force of attraction, or repulsion, between two particles, and is given by the following equation. F equals Q1 times Q2 all over R squared. Q1 is the charge on particle 1, Q2 is the charge on particle 2, and R is the distance between the two particles. A highly modified version of Coulomb's law gives the potential energy associated with the interaction between two particles. Thus the potential energy V is equal to K times Q1 times Q2 all over R. Potential energy in this case is more useful to us. K is a proportionality constant that we don't have to worry about. Q1, Q2 and R have the same meanings as in the original Coulomb's law. Notice that the R term is not squared in the energy equation. In an atom, we can consider Q1 to be the nuclear charge and Q2 to be the charge on an electron. Thus, for the hydrogen atom, we would calculate V is equal to K times plus 1 for the proton times minus 1 for the electron all over the distance R, and we would get negative K over R. Therefore, the potential energy is a negative quantity. If, however, the two particles are the same charge, then the potential energy value is a positive quantity, and we would have plus 1 times plus 1. This may seem odd, but as we shall see, it fits into the overall picture quite nicely. Now we turn to ionization energy. The ionization energy, IE, is the amount of energy that is required to be supplied to an electron that would cause it to be removed from that atom. In other words, the energy required to move the electron in its shell around the nucleus to a distance that is infinitely far from the nucleus. We can represent it like this. So we have an electron circling around the nucleus, and we supply enough energy to take that electron away. For now, we will focus on the first ionization energy, which is the minimum energy required to remove the first electron in that atom, or the easiest electron to remove. We can represent that by the following equation. Atom A becomes A plus having lost an electron. This is IE1, the first ionisation energy. The key thing to note at this point is that energy has to be supplied to remove the electron, so the ionisation energy is a positive value. The reason for this is that we need to supply energy to overcome the force of attraction between the nucleus and the electron. It turns out that there is a relationship between the potential energy of an electron and the ionisation energy. It is V equals negative IE. In other words, the value of the potential energy is equal in magnitude but opposite in sign. So for example, if the potential energy was negative 10 joules, then the ionisation energy would be 10 joules. In numbers that we're more likely to see, the potential energy could be negative 0.52 megajoules, and the ionisation energy would be plus 0.52 megajoules. We could represent this in a diagram as shown here, where our scale is the potential energy. The potential energy of our electron is found to be negative 0.52 megajoules, and it requires 0.52 megajoules to remove the electron. In other words, to take it from the starting point to a point infinitely far from the starting point. Now we should be ready to look at the shell model itself.